Hello everyone, my name is Conor Gomes. I'm an R&D scientist here at Pion, along with the lead developer of SCISSOR. And I am presenting an incredible body of work that was put out by our friends over at AstraZeneca on predicting the human subcutaneous bioavailability of monoclonal antibodies using an integrated in vitro in-silico approach, where the in vitro approach is our SCISSOR instrument. We're going to review the workflow more in depth in the following figures, but really briefly, 8 different monoclonal antibody injections were introduced to the SCISSOR platform, and their release was tracked via Rainbow. The transmission values come from the detectors that are complementary to the turbidity LEDs that are found within the artificial ECM cartridge that can be seen in the image here within SCISSOR. This release and transmittance data was fed into a functional principal component analysis tool to create eigenfunctions and eigenvalues, as you can see here with the 2 functional principal components and their weight within each function. Those were used to create 200 iterations of an IV-IVC model, and that model was applied to the SCISSOR data to show that the SCISSOR release profiles and turbidity data could be used to create a more relevant bioavailability calculation as compared to monkeys. A more in-depth look at the individual release profiles and transmittance profiles that came from the 8 mAb formulations can be seen here. These profiles were then fed into some eigenfunctions, and those functions can be seen in figure D with the percent weights of each individual functional principal component analysis has on each of the individual eigenvalues of those functions. The range of the functional principal component scores can be seen in the following figure, where the range of scores of the internal mAbs can be seen, as well as that compared to the external mAb that was run within the SCISSOR instrument. These scores are then used to inform the self-validated ensemble model, which is here to predict subcutaneous bioavailability of mAbs. And again, of those 200 models, they show representative weights of each mAb's injection behavior on each individual model before averaging them together in the end. After the creation of this model, we can see in tile F that the SCISSOR and transmittance and release data when fed into this model had a better prediction of bioavailability, a better correlation with human bioavailability than the monkey data that was previously shown. And this last tile depicts the weights of each behavior and how they impact the bioavailability calculation, with the transmittance being the first principal component of transmission being the most important factor, with then the first component of the release being the second most important factor. The authors then elucidate to this transmittance being a major factor because when you do have unstable mAbs within a formulation, that would lead to decreased bioavailability. You will most likely get more mAb aggregation and more turbid events that occur at an injection site. Following self-validation of the model, validation with external mAb formulations was done on the model that was created. And the 4 injections can be seen in this figure with their release profiles and transmittance profiles shown. And the major takeaway here was, again, these external mAbs, when fit into the model, also showed a better correlation with actual human bioavailability as compared to the monkey models that are typically used. Figure 4 depicts how the authors were able to relate the behavior seen inside the SCISSOR and model and relate that to classification of low, medium, and high bioavailability of mAb formulations. The authors do a great job at representing where their model has been validated within these regions and a clearly labeled extrapolation zone. And we can see that the observed data all falls within that region. Additionally, not only does this data back up that transmittance is negatively correlated, the transmittance variation is negatively correlated with achieved bioavailability, but the model separation of these 3 classes shows that the variation, 90% of the variation between the data sets is captured, and the model can correctly identify low, medium, and high bioavailability formulations. And just really quickly, the correlations that were shown by tile D can be backed up by the loading plots for the 3 principal components, where we see that the transmittance is almost always negatively correlated with human bioavailability, and the release of a drug from the ECM cartridge is positively correlated with human bioavailability. And the last part of this study shows that the authors dove even deeper into the formulations and showed how each of the formulation components and characteristics were dictating the behavior inside of SCISSOR and therefore dictating the predicted bioavailability. This two-dimensional heat map shows each of the formulation components and how they are correlated to the SCISSOR behavior with a positive, neutral, or negative correlation. Really quickly, just some examples of some observations is that pH is not at all correlated with the bioavailability or transmittance that was predicted from the model, really because pH of a formulation is only indicative of the mAbs characteristics in storage conditions, not action within the human body. But things like, the isoelectric point and molecular weight were inversely correlated to how much release was seen in ergo bioavailability. And we all know that more volatile electrostatics on a mAb surface or larger molecular weights can lead to more downstream effects and immunogenicity within the human body. When zooming in on the components that are found within the formulation and the excipients found within there, the authors were also able to elucidate how each of these ingredients can positively or negatively affect the behaviors within SCISSOR. Really, the major takeaway is that it looks like the presence of histamine increases the rate of release while decreasing the variation seen in the transmittance profiles or decreasing the transmittance profiles. So if this model were generally applicable, which a larger data set is needed in order to validate it, it would seem to show that histamine is a fantastic excipient to include to stabilize monoclonal antibody injections. In addition to that, they saw a significant difference between the action of each different kinds of sugars when it was included as an excipient within these formulations. Thank you for sticking with us through that quick review of quite an impressive body of work that was put out this year by AstraZeneca. If you have any questions about the instrument's capabilities or any questions about Pion's instruments or analytical capabilities, please contact either me, a development scientist lead developer on the SCISSOR system, or the product manager for the SCISSOR platform, Imogen, and I'll see you. Thank you.